Okay, I was going to do all this. I'm not going to. I'm going to let this motivate what we actually do, which you can see up above here, but don't look. Okay, what's the limit as delta theta goes to 0 of r of theta plus delta theta minus r of theta, which is, of course, the expression we see here. Okay, what's the limiting value of that expression as delta theta goes to 0, because that's going to be the expression for the length of this side, or the approximate expression for the length of this side. And that approximate expression is going to approach the exact expression as delta theta approaches 0. So we want to consider the limit involving this difference. And that obvious limit, if you think of the definition of the derivative, which you might not immediately think of here, it's been a while since you really thought of it, there's a definition, okay? What's this limit? It's a derivative. R prime of theta. Okay? So, we can take this and say that, say that R of theta plus delta theta, I didn't write it all out, sorry. Trying to get it squeezed in there, so I just left half of it out. I have to write it down here. R of theta plus delta theta is approximately equal to R of theta plus R prime of theta delta theta, because you can see that if theta is very small, this is very close to this. So that this minus this is very close to R prime of theta times delta theta. Add the R of theta to both sides, you get this. And at this point, you want to think about reviewing what the differential is. Or tangent line approximation. Two very closely related concepts that if you really understand, you would tend to immediately pull out. And I've said many times that differential is an obvious concept from first year calculus that nobody who's had first year calculus ever remembers. Well, one person in 1,000 maybe. When they take second year calculus, okay? Maybe 1 in 100. Maybe even 1 in 50, but not many. Okay. And I was still pondering. I mean, I kept pondering the idea of differential after first year calculus until it finally totally made sense, and I could apply it to things by the time I got to the end of the current course, the multivariable course. Okay. Calculus 3 these days. Okay, well, how is this going to be useful? Well, it'll be useful. We can plug it in here for R of theta plus delta theta, have to square it and all that stuff. We plug it in here for R of theta plus delta theta. So we're going to get some delta theta squareds and stuff, okay? We do all that. But, and I kind of recommend doing that as an exercise and thinking about what it means. However, much easier to do it here. Because now this expression, it's squared, just becomes square root of this, okay? And it becomes much simpler. So for R of theta plus delta theta, we plug this in. And of course, we could have plugged R prime of theta delta theta for the difference. R of theta plus delta theta minus R of theta here. Okay? Well, we've got to plug this in, though. So we get okay, we've got this. Well, that equals the square root of, or is approximately equal to the square root of, and when I say approximately equal, again, in everything I'm doing here, I mean approximately equal in the sense that as theta approaches 0, the approximation approaches being exact. So, r of theta plus delta theta is r of theta plus r prime of theta delta theta. Then it's minus r of theta. Okay, I mean this is your r of theta plus delta theta approximately. And you have your r of theta, and you want to square all that. And we have this. And of course, simplifying this, getting a little hard to read, better chalk. And yeah, maybe I need to write more carefully too. Well, this expression is exactly the same as this, because the r of theta is here, subtract off, you get r prime of theta delta theta, quantity being squared. And of course, we write out the square, we get the square root of r prime of theta squared times delta theta squared plus r squared of theta times delta theta quantity squared. And this is all very straightforward if you remember what a differential is, understand it, and invoke it. But there are a lot of steps here that are not going to be totally obvious to many students at the level of this course. And students who were there in class did a really good job of putting things together, but had to finally give some hints. Okay, so here we have the expression, which I'm going to write just to make it a little simpler to see. Could have done this much earlier, but just suppress the functional notation on theta, understanding that r prime and r are both functions of theta, which we've reinforced a number of times. Now, how do we simplify this expression? Well, if you've done a sufficient amount of simplification in intermediate algebra, much less pre-calculus or anyplace else, you see that you can factor out delta theta squared underneath the radical, which is the same as having a delta theta outside the radical. In other words, factor the delta theta squared out, and you get r prime squared plus r squared times delta theta squared, quantity times delta theta squared. And then, since the square root of a product is the product of the square roots, you're going to have the square root of this times the square root of delta theta squared. The square root of delta theta squared is delta theta. So now this is the quantity that you end up integrating. Now, it's easy to say integrate this, but I want to go on and show how the integral is set up. So if we want to find the arc length between, say, here and here, what's the integral going to be? If we want to find the area of everything from here to here, everything in this sector, how are we going to do that?